This video will attempt to talk you through how to recognize a perfect square trinomial and then factor it. The standard form of a quadratic is ax squared plus bx plus c, where a is the lead coefficient, c is the constant, and b is the linear term. So I've got a little mental checklist over here in blue, and it's not as complicated as it looks. When you're looking at a trinomial and you're trying to determine if it is a perfect square trinomial, look at A and look at C. A and C must both be perfect squares. And they should both be positive. They should both be positive. And this is the most basic type of perfect square trinomial to recognize. So if that's the case, if they're both positive and they're both perfect squares, then move to the linear term. And one way to think of it is b 2 times the square root of c. And that sounds complicated, but let's look at here. C is 9 in example number 1. The square root of 9 is 3. Is b 2 times 3? So 2 times 3 is 6. If b is 2 times 3, then that means that this is a perfect square trinomial. And the way that I would present the factors, m squared is a product of m times m, and I know that 9 is 3 times 3. I look at the sign on the linear term. If that sign is negative, then that tells me that I started with m minus 3 times m minus 3, because negative 3 times negative 3 gives me positive 9. So if I have subtraction, if I have the two perfect squares in the a and c spot, and if the coefficient on the linear term is the square root of c times 2, then I can assume that this is a perfect square trinomial. I create my binomials, and I let the operation in my binomials be dictated by the sign on the linear term. Now another way to look at this, and I'll change ink colors. So once again, you would definitely do your checks. Do I begin and end with perfect squares? And then you could look at the term in the middle. I've got negative 6 is the coefficient that on the linear term. Is 1/2 of 6 equal to, is 1/2 of 6 squared equal to c? So 1/2 of 6 is 3. Does c equal 3 squared? And if it does, then you can assume that you've got the perfect square trinomial, and then you can let the sign inside your binomial factors, that sign, or that operation rather, is dictated by the sign on the linear term inside the perfect square trinomial. Let's look at another example. And with a lot of things in math, it takes longer to explain and more words to explain than it actually does to use and recognize once you start using this. So let's look at number 3 together, okay? Do I begin and end with perfect squares? So I have positive g squared and positive 49. They are both perfect squares. Is the term in the middle the square root of 49, which is 7? Is the term in the middle 7 plus 7, or 7 times 2? Is my linear term 14? And yes, it is. So I open up my binomials. I have g times g and 7 times 7, and the operation is negative 14. So that tells me that the operation inside each binomial factor would be subtraction. Okay, let's look at another one. Let me erase all of this and we'll look at some on the other side. Okay, let's look at number 2. Do I begin and end with perfect squares? R squared and 4. The square root of 4 is 2. Is b, that number doubled, is b, and b is 4. So this tells me that this is a perfect square trinomial. And in my binomial factors, I start with r, and then I'm going to have 2. And I notice that the operation in the perfect square trinomial on the linear term, the operation is positive. So that tells me that the operation inside each binomial factor would be positive, or addition. Number 4 is not a perfect square trinomial because 2 is not a perfect square. So this is what I would call prime, irreducible, something I cannot factor. And we'll talk about that in class. Irreducible or prime. And then the problem with that is that the coefficient on the quadratic term is not a perfect square. Let's look at number 6. So in number 6, is 9n squared a perfect square? 9 is a perfect square, n squared is a perfect square, so it passes that. 25 is a perfect square. I begin and end with both positive numbers. So the only thing I have left to check, and here I could go ahead and set up binomials and then check. So 9n squared is going to be the product of 3n times itself. 25 is 5 times 5. The operation on the linear term is positive, so that means that I must have had plus plus 2 additions in my binomials. And I still need to check out that linear term. So I have 3n times 5 and 5 times 3n. Does that sum to 30n? And it does. So I assume, yes, this is a perfect square trinomial, and 3n plus 5 times itself would be the factored form of that perfect square trinomial. Let's look at a few others. And let's look at number 5. Is 4d squared a perfect square? 4 is a perfect square, and d squared is also a perfect square. Positive 1 is also a perfect square. So to test this out, I could open up my parentheses. I'm going to start each with 2d, and each would have positive 1. Notice that the operation or the sign on the linear term is negative, so that means that my binomial factors would both be subtraction, and I still am going to test out that term in the middle. So I know I'm going to have negative 2d and then negative 2d, and they will sum to negative 4d, which is the linear term. So number 5 is a perfect square trinomial, and it's 2d minus 1 squared. Let's do one more. We'll look at some of these in class, but let's do number 9. I just want to keep the video pretty straight. Number 9. So I start with the perfect square here, and I end with the perfect square. They're both positive. So the square root of 36 squared would be 6t. So let's set up my factors for testing. And then the square root of 4 is 2. The sign on the linear term is subtraction. So that means that my binomial factors will both be minus minus. And I just need to test out that linear term. So I have 6t times negative 2. And then I have it one more time. And that does sum up to negative 24t, which is my linear term. So the factored form of number 9 would be 6t minus 2 squared.